Hello, everyone. My name is Jay Metz, and I am here with Christine McMonagle. Christine, did I say
Good
your name
morning.
right?
Yep,
Yes.
that's right.
Hey, woohoo! Excellent, awesome. Alex McDonald from NetApp is going to be joining us in a little bit. Unfortunately, he's having a little bit of technical difficulties. But today, we are going to talk about the networking requirements for hyperconverged infrastructures. At least, that is where this plane is going, and if not, you're on the wrong plane. So, before we get started, I want to thank Christine for joining us on this. It's the first time I've worked with her on the presentations. Christine is obviously from Intel, and is going to be talking a bit more about some of the hyperconvergence elements that are useful to know. I am a member of the SNIA Board of Directors, and I'm also working for Cisco. And NetApp is officially represented by Alex McDonald today. He's going to be coming in a little bit as well. So to that end, just want to give a couple of things about the administrivia before we get started. And realistically, I'd like to be able to share with you that we are encouraging people to pay more attention to possibly joining SNIA. We've got over 185 organizations already involved. That number is a little bit out of date. A lot of active contributing members, and many, many end users and storage professionals worldwide. By the way, as we get into the technical bits of the legal notices, on occasion, there are people who have problems listening in to the session. What we have found sometimes is that there may be an issue with the caching of the browser, so clearing the cache in the browser can often help with the audio in case you wind up having those kinds of issues. Also, it's also worth mentioning that at the end of the presentation, we will be providing you with the link to the PDF of the slides, so they will be made available to you. And any member company or individual members can use the material from those PDFs or blogs, as long as none of the slides are modified and that SNIA is acknowledged as the source of the material used. Having said that, this is basically for your benefit because we love you. And so, as a result, no warranties expressed or implied are, well, warranted. So you can use at your own risk. And so, excuse me, I need to cough for a second. With that in mind, we're going to get started real quickly, but as you can probably imagine, hyperconvergence is one of those places that has fierce loyalty, both amongst the employees for different vendors as well as for the people who use them. And so to that end, this is a vendor-neutral presentation. And as a result, we are not going to be making any particular prescriptive recommendations, either expressly or implied. This is also a technology-neutral presentation. So we're not going to be creating any value comparisons. We're not going to say one technology is greater than another. We're not going to start doing this, oh, this is so great and this is so bad kind of a thing. We are going to be talking about some of the differences in implementations, however, but we're not going to be giving any kind of value comparisons. And finally, cannot stress this enough. We are here to talk to you about the networking impacts of hyperconvergence, and nothing in this presentation supersedes, overrides, or overwhelms your vendor's best practices and recommendations. One of the things that you will find when you are doing research about different hyperconvergence solutions is that there's enough of a difference between each of the different vendors and the reasons why they do what they do to make that vendor's recommendations very specific. The whole purpose why we do hyperconvergence in the first place is because of the fact that you want to simplify your system. So do not take this as a guide for how to override your vendor's best practices. You always want to follow those recommendations. So as we get started, the question has come up, why do we do this? Why are we doing this particular presentation? And the answer is because of the fact that when hyperconvergence came out, the answer we were trying, or the solution we were trying to solve for a particular problem was that we really needed to be able to simplify things quite a bit. And so over time, we have come to find out that because of the fact that most of the people who implement hyperconvergence tend to be more familiar with virtualization and compute, they may not have the kind of background into networking that they may wish to have. And as a result, you could have some unintended consequences coming up. And because of that, we decided that we're, as the Networking Storage Forum for SNIA, we're going to try to fill in that gap. We're going to try and discuss what is typically overlooked. Now, one of the things that's actually kind of amusing if you think about it, especially if you come from a networking situation, is all the different misconceptions of what happens with the storage. And if you start looking through the guidelines and the installation guides, this is really true when it comes to hyperconvergence vendors. They talk about how to do the configuration. Excuse me. They do the configuration, but the network is kind of assumed to be there. And all of the assumptions that people get wrong about the network, that it's always reliable, that it's always there, that the latency is zero, that you have infinite bandwidth to play, and that it never changes. All of these different things are something that can catch you out. And I include a quote from Tom Hollingsworth that I think pretty much underscores the big problem that people wind up having, which is that the assumption that networking is there is really not just a misunderstanding. It actually leaves you open to problems. So we have to focus on the interconnects and understand how that can actually affect your overall system. Now, having said that, we have a pretty robust agenda to get through. And the key thing is that we're going to try to give you a broad understanding about some of the concepts you have to keep in mind. And we're going to start off at a really high level, and we're going to dig deeper into some of the more specifics as we go along. So to start us off, Christine is going to be helping us with the basics of what is hyperconvergence and why we should care. So, Christine.
Yeah, thanks, Jay. I'll dive right in here. Do a brief level set on what is hyperconverged, how is it being used, and what are the implications of that from a networking perspective. So let's get going on this. So first, from a storage perspective, we wanted to talk briefly about where hyperconvergence fits and where its sweet spot is. There's a wide range of different storage solutions available in the market, and not every storage solution is meant to fit every application or meet every requirement. And there's sort of three vectors here that we look at, and those are manageability, scale, and performance. And understanding where hyperconvergence strengths are is part of what we wanted to share with you here today. So when we look at hyperconvergence, we really see it as being strongest on the manageability front. I don't want to give the impression that it doesn't deliver performance or scale. Certainly its performance is suited for a wide range of workloads in the data center, but there are more performance solutions that are available from a storage perspective. Similarly, on the scale side, hyperconvergence is a scale-out architecture and does scale out to many nodes, but there are more highly scalable software-defined storage solutions that can be deployed. It's really this manageability aspect where hyperconvergence has hit a sweet spot and proven to be easier to deploy and easier to manage than some of the other solutions out there. So let's look at this in a little bit more detail. So hyperconvergence is really a type of software-defined storage. And what it's doing is it's using standard servers, standard server hardware that each provide compute and storage resources. and it's clustering those servers together across a standard Ethernet network, and then pooling the resources of those storage devices and of those compute capabilities into a single pool of virtualized resources that can be accessed throughout the cluster. It's running with a hypervisor, and it can be delivered up as either block or file storage depending on the vendor. But the other key point is that the control plane is separated out from the data plane or flow, and the control is typically managed with the VMs through a hypervisor. So the magic sauce, if you will, here is that each node is talking to each other node. The management of these resources are virtualized and pooled together, and it's typically a pretty intuitive UI to deploy and manage the VMs and the storage resources together. So why are people deploying hyperconverged? Technology Business Research does a biannual survey of users of hyperconverged to find out why it is they're deploying it. And they found in their most recent survey that was just published at the beginning of January that 27% of enterprises have already deployed hyperconverged, and another 21% are planning to adopt it in the next year. And some of the reasons they're doing that are things like replacing hardware that they have already that's outdated, or they're using it to reduce both their CapEx and OpEx costs. Also popular were that they've run into management challenges either on the compute VM side or on the storage side, and they see hyperconverged as an easier way to manage those resources in their data center. Lack of IT resources, I'll talk more about this on the next couple of slides, but one of the advantages of hyperconverged is that it doesn't require a specialized storage skill set. And so it can be deployed by anyone with experience in managing a virtualized environment. And because it can be easily deployed and managed, you see it addressing that provisioning takes too long, or it's meeting the needs of a specific workload. So that's why people are deploying it. Let's look a little bit more at the trade-offs here, the strengths and also the challenges associated with hyperconverged. So talked already about how it virtualizes these resources and pools them together, so it's efficient from that standpoint. And then the data gets distributed across all of the nodes in the cluster, which leads to high durability. Scaling is in a typical scale-out modular fashion where you're adding additional servers each time you want to scale, and that's scaling the performance as well as the capacity. As I mentioned earlier, it can support a wide range of workloads in the data center and multiple workloads, and I've got some good data on that. And it can be managed using these familiar virtualization and hypervisor tools that a lot of people are already familiar with, so it doesn't require a specialized skill set. It's typically pretty rapid to deploy, and because it's a scale-out architecture, you don't have to invest everything up front. You can start with a small cluster and then add more nodes as those additional resources are required. So that eases the budgeting cycle. But despite those strengths, there are some challenges with hyperconverged as well. First is that you're typically one vendor only per cluster, and I mean one software vendor. You can't mix and match software solutions within a cluster. Hardware flexibility can vary. Some vendors offer a fairly wide range of hardware options. Others are more tightly coupled in an appliance model that's less flexible. And one of the things that I've heard more and more as people are more widely deploying hyperconverged and using it for additional workloads and adding nodes over time is that it can be difficult to balance the compute and storage, particularly as you're adding additional applications and workloads onto your cluster. it can be hard to manage that balance of compute and storage resources so you don't end up being either too compute heavy or too capacity heavy. And then, of course, some of those workloads, if they're more demanding or more latency sensitive workloads, can actually compete for resources with other workloads running on the cluster and perhaps outcompete them in terms of hogging some of the resources. Although most hyperconverged solutions do allow you to set some type of prioritization in the workloads that are running on your cluster to help, help address that. Suitable for a wide range of use cases, but not necessarily everything. If performance is a key concern on a data lake, for example, and analytics workloads like Hadoop, then hyperconverged may not be the best fit for that. It can certainly deliver ease of management and easy deployment of that big data workload, but may not deliver to the performance of running that on a bare metal. And of course, and this is what we're going to focus even more on today, is that as your cluster grows, you're placing added burden on the network, and those network resources become more and more critical to the performance of the overall cluster. Here's some more research from results from TBR, and you can see here on the right side the average number of nodes that people are deploying in a typical hyperconverged cluster. Clusters typically start at 3 or 4 server nodes. There are some vendors that have a way for you to do like a small 2-node cluster at an edge location, but those are typically not truly hyperconverged. They kind of reverted back to a failover type of mechanism you might see in a more traditional small SAN. So typically to get the level of durability as data is distributed through the cluster, clusters start at 3 or 4 nodes, can go as high as 128, but you can see here in the graph on the right, the more typical number of nodes people are running are in the 4 to 12 range. And of course, different solutions have different levels of scalability, so check with your software vendor as you're evaluating solutions. But in general, the larger your cluster grows, the more nodes you have, the more network traffic you're going to have, and the more demands that cluster is going to place on your network infrastructure, especially from a control plane perspective. And Jay will dive into that more deeply later. Which workloads are people typically running? Well, I've been working with hyperconverged partners of Intel for 5 or so years. And initially, you would see people really running secondary types of workloads on their hyperconverged clusters, things like desk dev environments or VDI. But as people get more and more comfortable with hyperconverged and understand its capabilities better, the number of workloads and the types of workloads people are running has grown. And what we can now see in the data from TBR on the right side is that database management, business intelligence and analytics, ERP, critical primary workloads for a business are the most popular workloads that people are running on hyperconverged clusters today. And of course that has implications from a networking perspective because secondary workloads are less of a concern in terms of how they tax the network or how they perform. But as you get to these more business critical workloads, the expectations in terms of performance and latency are very different. Mixed workloads are also very prevalent. And you can see in the data on the right here that people are often running half a dozen or more workloads simultaneously on their clusters, which places additional demands on the network. And some of the hyperconverged solutions on the market set up a data locality preference to try and co-locate a workload or application with the data that workload is using. But the greater number of workloads that you place on your cluster, you can imagine that it would be more and more difficult to try and co-locate them. Despite that, most of the HCI solutions do allow a level of prioritization where you can determine how critical a workload is and whether it should be given priority in terms of the compute resources and in terms of the network performance as well. Okay, so I'm going to hand off to Jay here to dive deeper into the storage characteristics and how hyperconverged solutions perform on that.
Excellent. Actually, before I start into it, I noticed that there is a question that came in about one of your earlier slides. So I'm going to actually go back a quick second. Question asks, why did most workloads usage drop between first half of 18 and the second half of 18 survey? Do you know why that may be? I haven't read this study.
Yeah. So they're seeing what percentage of respondents use certain workloads, and they've added. You can see in the light blue bar about 2/3 of the way down here. They added an edge compute, and I think that pulled away some of the users from some of the other categories. Maybe previously they said, well, we're running some edge analytics, and they put it in analytics, but now I think it's dropping into that edge bucket, which I think better allows us to understand how and where the workloads are being used. So I think that pulled away from several of the other workloads that are running in an edge or perhaps a retail location into that new bucket that they've added.
I see. Okay. Well, that makes perfect sense. I think it also underscores the fact that the workloads are not static. They don't stay the same, and they change over time.
Right.
And so that is actually, in all the conversations we've had up until this point, that's actually a really key factor that we haven't even discussed. So that question actually helped us illuminate a very specific point.
Yeah, it's definitely evolving.
Yeah, it is, and unfortunately, that also means that there's an impact. There's a consequence. There's an impact on what happens with the overall system. Before I move forward, I want to encourage you, audience members, to ask questions. If you should look for the ask a questions, and so we're not. There are a couple questions coming in about that survey. We're going to have to put that into the Q&A blog, which we're going to be able to use at the very end of at the end of the webinar. We'll put together a Q&A blog and talk about some of the questions that we weren't able to get to on the presentation. But please do ask those questions, and we will get to them as we can. And if not, we will certainly put them towards the Q&A blog afterwards. Got a couple of comments about audio. Did a quick check. We're not really having any audio problems, so that could be something in your browser. You may want to check your browser or your phone settings. Okay, having said that, let's go ahead and talk a little bit more about the storage characteristics. Because in this section, we're going to take a look at some of the key characteristics of storage when it comes to hyperconvergence. In particular, we're going to be discussing the ways that the host relates to the target and the impact of virtualization on that storage I/O, as well as a few other things. So let's begin by talking about some of the overarching characteristics of hyperconverged that make it different from other methods that people may be familiar with. So earlier in the presentation, we talked a bit about some of the key aspects of storage that dictate the kind of solution that you're going to find. Some of the solutions are highly performant, some are highly scalable, and some are better at management than others. All of the systems, though, have one key job that supersedes everything. Do not lose data. This is the most important thing. So it's useful to know how these systems actually do this in their own way. Now, we can't really talk about how hyperconvergence does this without talking about how it moved from a particular way of doing this, especially as we start to look at the networking elements here. In traditional storage environments, a host is connected through a switch to a storage device. This is a broad general view of how a SAN works and how a NAS works. network attached storage. It's also generally referred to as centralized storage, as all of the storage is physically located in one place. The reason why this was done was because historically it was easier to manage categories of technology, whether they be compute, networking, or storage, instead of managing lots of individual independent devices. As these systems began to grow and scale, often to the tune of thousands of devices, it was better to manage them independently and use standard protocols to communicate between them. Each layer then was responsible for not only the management, but also the protection of that data. No one was off the hook. Every one of them had to make sure that no data was lost, so high availability was built in at every section. So hypervisors were responsible for their area, networks were responsible for theirs, and storage was responsible for theirs. So one of the important things to know, though, is that it was remarkably easy to see just what the impact of these devices were on one another. For instance, it was easy to see just how much bandwidth their host was taking up, or just how much bandwidth a storage device was able to cope with, or how much bandwidth the network could handle as a system. And because of the one-to-one relationship between the hosts and the targets, we could also measure latency. And even if it wasn't always to troubleshoot, congestion was better understood across the whole system. Now, with hyperconverged storage traffic, on the other hand, this changes the nature of the relationship between a host and its storage. Okay? It actually brings it back into the box. It brings it back into the server. And the key advantage here is the ability to also create an abstraction layer between the host and the storage that can be extended across multiple physical devices. Now, earlier we had a headache when we were trying to manage these individual devices, but this way we can avoid that management headache. And so it's great. Unfortunately, it also increases the amount of traffic that has to go between these boxes, and that's also called east-west traffic. Now that means as well that when you scale, you don't scale north to south. You have to scale east to west. And when that happens, it plays against the performance. Now the reason why it does this is that in order for storage systems to be performant, you want to have them as close to the compute as possible. Now in turn, that means you can't really oversubscribe as readily. So every oversubscription represents endpoints and exchanges. So each time you add a node, you add another piece to the network. Whereas in a north-south environment, you can add links, but it's more difficult to do that inside of a hyperconverged system. And the link speeds don't change. So as a result, every additional node adds some level of a burden onto the network. Now it's important to remember that because hyperconverged systems have the same requirements as every other storage system, namely, don't lose data, all data is distributed to multiple nodes and load balanced. That means that when you increase the nodes, it also increases the overall bandwidth requirements, not just for the overall node traffic, but for the load balancing traffic as well. And we'll get to deal with these different types of traffic a little later on. Okay, obviously, HCI hyperconvergence follows the same rules as everything else. The simpler it is for the end user, the more complexity gets hidden underneath, kind of like doing these webinars. But here, the goal is to make I/O transparent to the application. We don't want the application to know what's going on underneath. We just want it to see a storage device in its own native format. So the man behind the curtain, so to speak, does all the magic about distributing the data to where it goes. And that layer of coordination has a trade-off of providing the simplicity and ubiquity to the applications in the management layer, but the added work of ensuring that the communication between the nodes is safe, secure, reliable, and predictable. So in order to do this, the management software on the node, and it can exist in hardware or software, has to handle each I/O, the real I/O, and determine what to do with it. So heavy workloads with distributed data don't deal well with delays. And so for that reason, we treat reads and writes in a system slightly differently. Okay? When a read comes in, for instance, it has to know where the data is held, and therefore it asks for it. Now, obviously, it's more helpful if the data is stored locally on the same node that the virtual machine is on. This goes back to the part where performance really is better the closer the storage is to the compute. However, it can't always be guaranteed that the local storage device holds the needed data, or that even if it does, it's the fastest way to get it. So what ends up happening is that we need to create a priority, an importance for reads that have the lowest amount of delay, the lowest amount of latency. Now, for writes, though, it's a little bit more involved. The approach to solving the do not lose data requirement, it can vary. But in general, writing to storage devices can be made much more efficient by concatenating the write IOs and sending them out in a batch. At the same time, you can do some nifty additional things such as compression and deduplication, so the trade-offs with the delay can be worth it. And so to that end, when we start to look at I/O in particular for HCI, how the data gets written can make a huge impact on the overall performance of the system and where that data is located, to going back to Christine's point earlier on about the different workload mixes and so on. Okay, so obviously we've been talking about the ability to virtualize and abstract entire environments. And you also have heard that NVMe makes everything better. So what happens when you combine NVMe and HCI? Well, it's useful to remember that every virtual bit also has a real bit underneath. So it becomes useful to know just what will happen when you start to add in some high-performance components into the mix. Now, what tends to happen is that when you swap out one component for another, the bottlenecks don't simply go away. They shift from one place to another place in the system. When you add in flash, or more recently NVMe storage into the solutions, you can indeed get more I/O out of specific nodes. And obviously that is good for the nodes. What it does, though, is add additional pressure into the network. As a result, the network becomes a bottleneck unless you plan for it. NVMe, for instance, is an incredibly efficient and high-performance storage protocol, and NVMe over Fabrics extends that efficiency and performance over a network. And that means that when NVMe over Fabrics becomes available and eventually more prevalent, you will see that the network requirements are going to be even more important than they are already. As we've been saying all along, different vendors support different technologies, but you should always watch for stressing the network with these new components, especially for those solutions that are purely software-based and allow you to choose your own hardware. It's worth pointing out, by the way, that SNIA has done a lot of presentations about this already. If you're not already familiar with how NVMe over Fabrics works, you might want to take a look at the under the hood presentation that we've done a little while ago. At the end of the presentation, this one right here, we'll also have some more links to additional webinars and blogs that cover this topic in greater detail. It's useful to remember that everything is related to everything else. And so understanding the different components can make your own life a lot easier over time. Okay, so speaking of I/O, one of the consequences of virtualizing it is that there can be a mismatch of I/O characteristics between virtual machines and their corresponding applications. And applications tend to think that they have the I/O channel all to themselves, and they don't. And this is also called the blender effect. And there's an excellent blog series on the subject by Stephen Foskett about this that I highly recommend. The link is listed below here at the bottom of the screen underneath the graphic. So I do recommend that you check out that one because it's beautiful. It's a wonderfully described blog piece about how this works. As I said, the virtual machine has no idea about all of the I/O, and something has to be done to do the demuxing, and that is the responsibility of the hyperconverged solution. From the application's perspective, it's getting direct blocked access to the storage, but in fact, it's being redirected by the hypervisor software to somewhere else. And that's where the noisy neighbor comes in, because the app thinks it's doing north-south stuff, when in fact it's actually going east-west. And this affects everybody, not just the neighbors. So in the truest sense of the word, the network becomes effectively a bus. It's not just moving the I/O data around. It becomes a giant toy box where all the interconnects and all the communication are thrown in, if you're not careful. And this is one of the key impacts for hyperconvergence over time. The more applications that you add, the more unintended consequences of the network impact that you're going to find. Add in applications with different I/O requirements in virtual machines on the same machine, and you can easily overwhelm the capabilities of the network, especially given the read and write scenarios we talked about earlier. So there are some of the things that you can do to help mitigate this, however. One thing you can do is create specific applications on specific nodes for avoiding this kind of contention. Christine actually mentioned this explicitly earlier on. Now, you'll have to check your favorite vendor's documentation to determine if and how to do this, of course. Now, from the networking side, things like RDMA can help because RDMA bypasses the host CPU and gets rid of the buffering on the host, making the network more responsible for the I/O processing. And we've done, the Networking Storage Forum has done a couple presentations on RDMA and storage in particular.
And responsive,
So,
I think you could say too, makes the network more responsive to those traffic going over it.
well, yes and no. It makes it more responsive, but it also adds additional pressure into the burden itself. So we're reducing the pressure on the caching in the host memory and the compute cycles, and we reduce the amount of context switching that occurs in the hosts, but it does increase the burden on the network. So yes, it's responsive in the sense that it has more work to do, but there's a trade-off with, like everything else, there's a trade-off with there as well. So because of that, it's important to note that, where things actually fit in terms, even on the VMs, can actually profoundly impact the network. Okay, so block or file. At this point in time, I'm bringing this up because there's a tendency to have a huge religious debate over whether or not block is better or file is better. However, there are some very simple truths that are worth knowing. First, we're talking about a solution that is not dependent upon either the performance or the scale differentiations that block or file-based storage networks have. Really, where those things tend to fit in mostly have to do with, the north-south traffic issues and where the different protocols do their availability and that kind of stuff. We're talking about considerably smaller deployments in either of those systems, which have different oversubscription calculations. Because of that, for hyperconverged systems, the differences between block and file really don't matter. It's useful to remember that the workloads are typically put onto hyperconverged systems, and they have well understood network behavior and will have their own requirements for proper networking design. Now, second, we're back to the same caveat as before. Each vendor has its own recommendations. Some vendors allow for either block or file, and you can feel free to use whatever you're comfortable with. Just remember that you'll want to keep the same best practices that you'll get used to, whatever storage networking protocol you decide to use, and obviously you don't get something for free. So, having said that, I am going to take a quick pause. I see that we've got some questions that have come through, and it looks like some of the browser issues have been solved. HCI configuration ought to exist out of 3 or more nodes. Have I misunderstood this? Okay. So
I can briefly answer that one again if you want me to, Alex. I mean, Jay. The I think I talked about that. I think I talked about that to really have a true hyperconverged solution that needs to be 3 or 4 nodes or more to really have the data distributed. But certain vendors offer smaller deployment options for edge locations that are a couple of nodes, and then they sort of revert to a failover type of mechanism instead of really distributing the data for durability.
Right. Right. They may be part of a broader ecosystem, but it doesn't constitute a cluster at that point.
Right.
Yep.
What about this
NVMe
over fabric question, Jay? about
Yeah,
NVMe
so
over Fiber Channel or other technologies.
right, and it's an excellent question. So NVMe over Fabric, I find it very interesting that the first transport protocol that is considered as Fiber Channel. My brother from another mother. Okay, so NVMe over Fabrics really is about the ability for NVMe to run over a different transport than PCIe. And yes, Fiber Channel is one of them, but it can also be run over RDMA-based networks such as Rocky and iWarp, or it can even be run over TCP. So NVMe over Fabrics means the ability to run NVMe over a transport, and just Fiber Channel happens to be one of them. And let's see, we've got a couple of different other comments. I'm going to have to postpone it now and try to get back to it because I'm looking at the clock all of a sudden and realizing that I need to move on. But excellent questions. Yep. Keep them coming, keep them coming, keep going. Okay, so where are we? Oh, yes, the agenda. Here we go. All right, so now we're getting to the specifics about the networks themselves. And after all, this is really what we're here for. So, as we've seen, HCI brings its own challenges and considerations because we don't simply treat networking or the nodes as isolated entities. That's the kind of thing we've done in the past, but HCI sees all of these things as part of one complete ecosystem. Now, speaking solely for myself, I can say that I have read recently close to 24 configuration and installation guides from a number of hyperconvergence vendors. There are a lot of differences and a lot of specifics, I think I just made up a word, a lot of specifics that are unique to each vendor. One thing, though, is very similar in all of them, and the network configuration for each vendor is extremely prescriptive. What I mean by that is that there's very little in any of the guides that goes into the reasons or the impacts that hyperconverged systems have on the network. It's also one of the reasons why we're doing this presentation in the first place. They simply tell you how to configure the settings. Now, all of this can lead to an interesting phenomenon, which is why we're repeating these concepts right here. It's worth repeating. You're encouraged to think of the network as just there. And even if the configuration guides don't say it explicitly, you'll need to remember that the network isn't infinite, and there is no such thing as zero latency. You have to remember that networks are never plug and play, and that much of the time the network will itself be far more heterogeneous than the hyperconverged systems that you're implementing. In other words, do not underestimate the network in general. Now, I've said before that, generically speaking, networks become one giant bus or toy box for all the traffic to be put on. In reality, though, some kind of separation between storage traffic and workload traffic is really important. And for that reason, different vendors will recommend at least separating the traffic into multiple different networks, at least two of them, either physical or virtual. There will usually be, like I said, at least two different networks. There'll be a data network and a management network. Now, some vendors actually break it down even further. They include a separate network for just the metadata, or a separate network for solutions that motion virtual machines or storage from one node to another. Some solutions recommend having different VLANs for the VMs as well. Now, Alex has pointed out to me that I need to remind something that people can take for granted, and that is that different people think of storage in different ways, and it's easy to forget that people measure things a little bit differently. Networks, for instance, is measured in bits, not bytes. So if you're not into the math and want an easy rule of thumb, you can divide the networking number by 10 and find out just how many bytes get transferred, right? So if you got a 10 gig link, it'll transfer 1 gigabyte, of data, roughly. We're talking about broad strokes here. I can imagine many people in the audience are probably groaning about the lack of precision here, I'm sure, but for quick and dirty calculations, it's good enough. If you want to do your oversubscription calculations, you're going to need to be a little bit more precise. But last but not least, remember that the storage interfaces are much faster than the network interfaces, and that the newer technologies like NVMe in particular can completely saturate the network links with data I/O, since every write must get written to a pair of nodes. So some vendors will recommend a completely separate physical switch to handle this load. The bottom line is that, anecdotally, it seems like 90% of the problems in hyperconvergence systems stems from the network, and you may want to consider requiring a dedicated physical network for storage. It seems to eliminate, at least anecdotally, the cause of a lot of headaches in practice. Now, having said that, your own mileage will vary, and you want to talk to your hyperconvergence vendor first before you make any drastic changes to your network. If you sense a theme here, it's because there is one. So, all of this brings us to the choices that you have for designing your own hyperconvergence cluster. Now, earlier, one of the graphics that Christine showed had to do with how many workloads are handled inside of a system. It also showed, another slide showed how many different nodes are included in the system. What is not clear is how many of those workloads are in how many of those nodes. So, some of the things to keep in mind. One option is to create small, purpose-built clusters with a limited number of applications or application types to be installed. And now in this way, you can fine-tune the specific services and ensure that you don't run into I/O contention issues. One of the key aspects of this is that you wind up with a smaller fault domain, and that allows you to isolate problems for your applications to a limited number of physical nodes. And because you tightly control the system, your networking implications become well understood. And since you're not throwing everything, including the kitchen sink, onto the system, your networking issues are likely to decrease as well, and as a result. Now, conversely, some people find that those purpose-built clusters are a little too isolating and prefer to work with larger mixed-use clusters. Now, obviously, there's some trade-offs here as well. So then again, you didn't really think that you're going to get away with not having to make any decisions, right? So yeah, you're going to have to understand these things a little bit better. So large clusters can offer some pretty interesting strengths. For instance, the more nodes that you have, the more protection and efficiency options you have that you can use. It also means that spreading out the pressure on multiple nodes, reducing the impact on those individual nodes. Now, because of this, it does require an increase in networking knowledge as well as understanding the network management and quality of service concepts. This, of course, leads us to what those concepts actually mean. When you look through the configuration guides, your hyperconvergence vendors will tell you what settings to choose and how to configure them for your particular setup. And of course, the reason why you bought hyperconvergence in the first place was for that simplicity. You just wanted to be able to set it up. Now, for that reason, you want to follow the vendor's guidelines to the letter. Now, for instance, if you're talking about small purpose-built clusters, most administrators are not networking engineers, and that's okay. Simply turning on the networking features that you're told to do is exactly the right way to do it. Now, that is ultimately the point. If your vendor tells you that spanning tree is required, or if they tell you that you're required to not use it, believe them. If you have no idea what a BPDU is, for instance, do not start messing around with your spanning tree sessions. Bad things will happen, I guarantee it. It is inevitable, though, that you will eventually want better performance from your cluster. You may hear that if you want to improve performance, turning on active-active load balancing in the network, or turning on jumbo frames, or bonding your interfaces, that sort of thing. You will hear this advice a lot. Resist the temptation to mess around with these settings. This is one of those places of advice that we will cast in stone. Do not start messing around with these network settings if you don't understand what they are or what the consequences are. If you absolutely, positively must change the settings, talk to your hyperconvergence vendor first. The last thing you want to do is slow your system to a crawl, or worse, because you changed an interface setting that is required for critical I/O. Trust me, bad things will happen. Which leads us to the final part. Were you going to say something, Christine? I thought I heard a breath.
No, I was just laughing in agreement.
Well, that's usually most people laugh at me rather than with me, so this is a good sign. Okay, so speaking of laughing, you can laugh yourself all the way into long-distance hell if you're not careful. Stretching a cluster. So this is where the propeller spins the other way. When you're talking about networking and data inside of a system, data center system, excuse me, when you start talking about that, you really have a lot more predictability and control over what's going on inside of the network, inside of the ecosystem. All right. However, when you start going out over a long-distance network, it's important to remember that stretched clusters, you're talking about treating two geographically different locations as if they were one. And all of the places where this becomes important to note about how your system does the reads and the writes, how it actually finds out where the data is located and brings it back. All of these things make an even more important impact when you're talking about doing this over a distance. Now, different vendors have different requirements and different elements for what they need. Some vendors only require a 5 millisecond maximum round trip time. Some are much more strict. They will require 2 millisecond maximum round trip times. And every single aspect of how the applications write data and read data becomes really critical, because we're not talking about disaster recovery here. We're not talking about business continuity. We're talking about a complete ecosystem that is treated as a single unit. So when you have these kinds of things, take a look at what you can do to mitigate the overall latency for the application reads and writes. Many of the solutions have SSDs or NVMe caching, and so the network itself will be the biggest problem. Consider dedicated WAN links and make sure that those WAN links are really well finely tuned. Try not to push it all the way to the maximum round trip time, right? Which is only a few dozen kilometers when you start to get into the 2 and especially the 5 millisecond rating. It's only about 60 kilometers if I remember my math correctly. But really, 60 miles, 100 kilometers. But realistically, it's expensive to treat these things as just there. This goes back to the point we were talking about of assuming that the network is reliable, assuming that the network is there. If you're going over an internet TCP connection to your remote data center and you don't have control over that link, this becomes even more obvious, right? So there's more than one administrator, there's more than one network link, and so on and so forth. And we can't necessarily bypass the whole, physics problem. So that brings us to the end of our situation. I know we have a couple questions. We've got, I'll get to those in a second, but really quickly, let me just go ahead and summarize the really important points here. Hyperconvergence offers a solution to a problem, and that problem is complexity. So it managed to take that complexity and put it under the covers. It gives you a great, ubiquitous, unified approach to viewing your system. And the trade-offs are that there are, consequences in various parts of that ecosystem. The network is probably one of the ones that is the most obvious. You do want to listen to the vendor. I mean, if there's anything that, is important, you want to make sure that you listen to the vendor. Evaluate your vendors beyond what the configuration guides say, beyond what the Salesforce search say. Understand how the reads and writes make a difference in their environment. Understand what that actually can imply when you start to put this into a system. Should you go with a small purpose-built system? Should you go with a larger system? Different vendors have different solutions with different sweet spots. So these are all part of the questions that you should ask. And in order to do that, you really need to understand the principles of what's going on. You do get the complexity hidden, but you should know that it's still there, and what you don't know can hurt you if you're not careful. So understanding how these things work, or becoming good friends with somebody who understands how these things work, can make you a better end user as well, and make your systems run a lot better and a lot smoother. I do want to pay particular attention to calling out a very special thanks to a number of people who extended their assistance and their help for this, and I've listed them here because, to be honest, I don't know if I would have been able to get as thorough of a session without their help. So I want to thank them profusely for that. So, we have a couple minutes. I see we have got a number of different questions that have come up.
Yeah, there's a question, Jay, on can you define metadata?
Yes. Okay. is probably a very important question that needs to be answered. So when you have data that goes from an application to a storage device, we call that effectively the I/O data. A hypervisor or a hyperconvergence abstraction has to have a lot of information about that data that they're transferring. It has to know where it's supposed to go, it has to know when it was written, it has to know where it was coming from and where it's going to, and all that kind of stuff. All that data that surrounds the actual I/O is called metadata. That metadata has to be transmitted between nodes. The way that you transmit it between nodes is that you have to put it onto the network. When you put that data onto a large system, it can actually be more data than the actual application is writing to storage. In other words, if you're writing three things to 3 different nodes, you have to have all that metadata go to 3 different nodes, and that information has to transfer back and forth. And in a hyperconverged system, it's not unheard of to hear of more metadata being transferred than the actual data the applications require. So, in order to compensate for that, some vendors require putting that metadata on its own network. And so, to that end, it's important to note whether or not you need a specific network for that kind of metadata transfer. And so,
we've also got a question. Oh, sorry. Can we move on to the next question? Well, we've got another couple minutes here, Jay.
Yeah, absolutely. I know what you're going to ask too. Yep, go ahead.
Yeah, so there was a question about RDMA and fabrics, and do we see fabrics as being required to be RDMA aware, and if so, who's going to do this?
So this is one of those layer 8 questions. So we see some vendors trying to allowing you to leverage RDMA, and this is unfortunately one of those ones that doesn't have a generic answer. It's going to be a requirement to talk to the vendor as to what kind of host offloading that is done into the NIC. Excuse me. So the advice that your vendor gives you about whether or not you can use RDMA, who is going to be responsible, is going to have to be a negotiation between you as an implementer and the actual vendor, as well as who's operating your network inside of your own company. There's a negotiation that has to go on internally, and unfortunately, there's no one
Yeah, there's multiple pieces, right?
Yeah,
but it's safe to say that you can't just do it on your own on a networking side and expect it to work. The hyperconverged solution does have to know how to take advantage of that. And this is an emerging technology, but we'll see more of it over time.
Right. And so one last question we have. We just hit the top of the hour. What do HCI vendors have to say about networking? This is a clarification question. The installation guides have a lot to say about networking configurations and installations. They have a great deal of information about where to go, where to put what port, where to put what VLAN. That's all part and parcel of the guides. What they don't talk about is what happens inside the network. They'll tell you how to configure it, but they don't explain why you're doing what you're doing or what the overall impact is, at least not in the installation guides. So if you do want to know about what the impact is, you really have to talk to them specifically and get their take on what happens inside of the network. So to that end, please don't forget to leave feedback. We do have the PDF available. I will put that into a broadcast right now, and we wish to let you know about the upcoming presentation. And I can't get this to work right. So I will.
Yeah, it's about scale-out file systems. Is our next webcast from the Networking Storage Forum at SNIA, and that's at the end of this month, and there is a link there.
That's right. That's correct. And again, please rate the webcast. We do thrive on your feedback. We apologize that we can't get to every single one of the Q&A questions, but we are going to put together a Q&A blog going over all the questions that we couldn't get to, including providing additional feedback and answers for some of the ones that did get covered. And of course, you can follow us for more information on SNIA NSF on Twitter. And we do want to thank you profusely for taking the time out of your day to join us. Christine, thank you very much for being on the presentation.
Yeah, thank you.
Great. Well, we're going to go ahead and conclude. I want to thank you very much for attending, and we hope that you found this useful. Thank you.